On Tomorrow's World Today, we explore the cutting-edge advances that are shaping 4 different worlds. The world of inspiration, where the wonders of the natural world amaze and inspire us. The world of creation, where ideas come to life from traditional arts. The world of innovation, where ideas and inventions move us all forward. The world of production, where innovations are mass-produced to improve our lives. From Inventionland World Headquarters, here's your host, George Davison.
What would life be like without copper? You probably haven't thought much about this, or even how prevalent copper is in our lives. But copper is believed to be the first metal ever discovered by humans, almost 10,000 years ago. Today, we use it in our homes for water and electricity. We even have it in our cell phones. Even though copper has been used as a conductor for electricity since the 1830s, how we mine it and separate it is constantly evolving. I'm going to send Greg to the world of production to explore this incremental innovation, specifically the technology used to evaluate and separate copper by type before it even makes it above ground.
Copper is everywhere. It's in the pennies in your pocket. It's in the car that you drive. It's in the satellites orbiting the Earth, even in the machines exploring Mars. Many of the things that we use every single day simply wouldn't work without copper. That's why we're here in Vancouver, British Columbia, to visit Teck Resources and find out about their innovative race technology, which is making copper mining safer, more productive, and most importantly, more sustainable. Because as important as copper is today, it's going to be even more important in tomorrow's world.
Hey Greg, welcome to our race office. It's good to see you.
It's good to see you too, Andrea. So I am here to learn about race technology, but I guess first things first, what does RACE stand for?
RACE is our business transformation program, and it stands for Renewing Our Technology Infrastructure, looking for opportunities for automation and robotics, connecting our data systems, and really empowering our employees. I'm going to introduce you to Andrew Milner, and he'll tell you a lot more about it.
Sounds great. You lead the way.
Let's go. Greg, I want to introduce you to Andrew Milner.
Andrew, great to meet you.
You too, Greg. How are you?
I'm great. Andrea, thanks a lot.
Take care,
Thanks,
guys.
Andrea.
So, Andrew, I now know what RACE stands for, but tell me about how RACE works in a real-world mining operation.
So the most important aspect of RACE for me is the E part. It's the empower piece. It's about the cultural transformation. It's about our people. So effectively, RACE is about 250 people working in this beautiful office that you see here, and 10,000 odd people out at our sites, all working collaboratively to transform the way we mine. And that means looking at our value chain, lowering variability, and basically being the most effective miner on the planet.
And sustainability is a big part of this too, because as important as copper is to us now, it's going to be even more important in the future.
Absolutely. We're one of the world's biggest copper producers, and that's going to be essential for all of the technologies that most people can see these days around electric vehicles and solar, etc. And so that's going to be essential for the green world that we're moving into.
Now, one of the aspects of RACE that I was reading about is the ore tracking system. How does that work?
So ore tracking system is a subcomponent of the RACE program. We have 200 odd initiatives. Ore tracking system is one that leverages machine learning, artificial intelligence to optimise a component of the processing value chain in HVC.
Okay, great. Well, I'd really love to see this in action. Is there any way I can get out to one of the mining sites?
Absolutely. Andrew can take you out to HVC. We've got a team waiting to meet you.
Sounds great. Andrew, thank you very much.
No problem, Greg. See ya.
Andrea, let's go.
All right, Greg, I want to introduce you to Carl Diederich. He'll take you down to the Valley Pit.
Hey, Carl. Andrea, thanks a lot. All right, Carl. Let's head down to the mine.
Hop in, Greg. Let's go.
Carl, this is amazing. I am really impressed by the size of the operation here. Now, but tell me, why are these steps cut into the rock this way?
The steps or benches are there to protect our workers from rockfall. So if any rock was to come off the high wall, it would get caught on that flat step.
Okay, well, what's the first step in the mining process when you're working in the pit?
So the mining process starts with drilling and blasting. You can see a blast hole drill. They drill a 12-inch hole. We load it with explosives and detonate the explosives, and that fractures and loosens up the rock. We can dig it with our shovel at that point, and we load it into haul trucks, haul it up to the crusher.
Okay, so the shovel, this is where the race technology that we were talking about really starts to come into play.
Absolutely. So all the information that we collect in the pit, the hardness from drilling the blast holes, the geology information that we have around the grade and the mineralization, that gets combined into a block model so that we know the qualities of every bucket that we're digging and delivering to the mill.
So all that data is collected before you even dig in the ground?
It is, yeah.
All right, well, I'd really like to see how that technology works in one of the shovels. Can we go take a look?
Let's take a look.
Without copper, our world wouldn't run, but we have to find a way to mine it in a sustainable way. I'm at the Highland Valley Copper Base in British Columbia, where we're exploring mining and sustainability. Well, Carl, when I think about a shovel, I think about the shovel I use in my garden. And this is clearly not that. So mining's come a long way since pickaxes and shovels. Explain to me about all of this innovative technology that's happening here.
We have a lot of technology on our shovels at Highland Valley Copper. Starting down at the bucket, we have X-ray heads in the bucket that can measure the copper grade. So as we're digging, we get a real-time readout on the amount of copper that's in each bucket. That helps us sort the material. So whether it's ore, it can go to the mill, or waste, it can go to the waste dump. On top of the cab, we also have a camera that measures the size of the rocks that are being dug. And that information helps us refine our blasting process.
Okay, so this is all part of the ore tracking system, basically, that on a bucket-by-bucket basis, you can tell what's going to be put into the haul truck, and that'll determine where that goes.
Yeah.
Okay, so tell me what these displays are showing us.
We got various displays in the shovel cab. At the top is the information from the X-ray heads in the shovel buckets. Below that, we have the GPS system, and that shows as what the material type initially was classified as, so whether it was ore or waste. It shows the shovel location, shovel elevation, mine design, anything that the operator would need to know. To the left is the dispatch system, and it shows where we're digging, the haul trucks that are being loaded, the material origin and the destination, so whether it's going to a crusher or a dump. Some general cameras to make it easier to see what's happening around this large machine.
So that's just the mechanical systems of the shovel we're sitting in?
Yeah, absolutely.
Okay, well, I mean, we've seen the haul trucks take off. They're heading to the crushers. I would definitely want to check that out. We need to let you get back to work, so let's head on out.
Great. Highland Valley's been operating since the 70s. Right now we're mining a pushback and we're about halfway down to the bottom, so it's almost 1,000 meters deep. We're running approximately 30 793 trucks every day. We run 24/7, so days and nights. The operations crew in the mines is roughly 70 to 80 people per day when you consider truck drivers, shovel operators, blast hole drillers, and all the support equipment, so graders, dozers, fuel trucks, etc.
Hey, Ryan.
Hi, Greg.
All right, well, Carl showed me the shovel, and that was pretty impressive, but now I want to see the domes.
All right, let's go have a look.
So on our way there, we see this conveyor. Now, this is pretty impressive with how long it is. Tell me a little bit about this conveyor belt.
Yeah, we've got a couple kilometers worth of conveyors before we hit the domes. So everything that's coming out of the crusher travels these conveyors all the way up to the stockpiles. We go through a number of switching points along the way that allows us to blend the ore. On top of that, we're also tracking with that OTS system, where that ore is going at any given time. When it hits the crusher, that's our first data point that comes from the pit. And from there, we track that ore all the way up to the stockpile and through the stockpile.
So this will actually help determine when it gets to the dome how that ore is then processed, because you have a couple of different processes based on grade. And this helps you to kind of optimize that so you're not doing that testing at that point. You've already got that information already sussed out.
Yeah, we're doing two real important things with the OTS. One, we're making decisions on where to put the ore and how to set up the switching points to get it on the right stockpiles. We're doing that with respect to hardness, try and maximize throughput. And we're also taking all that OTS information and then using it for flotation as well. We want to know what quality for the ore that's hitting the grinding mills, and we're making decisions in floats on how to best recover it.
Okay, so it's really about optimizing that ore to its best ability.
Exactly. We're trying to maximize recovery, maximize yield.
Okay, well, let's go see the domes.
Okay, yeah, we'll travel under this first switching point, head that way.
Well, Ryan, we made it here to the domes. Now, this is the next step in the OTS, or the ore tracking system. Tell me what's happened since we left the crusher.
So since we left, we followed that conveyor belt all the way up here to the stockpiles. You know, we've got a couple kilometers worth of conveyors between the crushers and the domes themselves. When we first built the OTS itself, we originally had 20,000 RFID tags that we sent through the conveyance systems. Those went through the domes and through the grinding mills below us. And those were our data sources, or data, if you will, that were used to create models that would model the different chutes, model the domes at varying pile heights before it would go into the mills and they'd be destroyed.
Oh, so that's really like how you decide, like with the different grades of ore, what might be the best, end use for those.
That allowed us to, like I said, create those models, track those ore attributes from the crushers through the blending points, into the stockpiles, through the stockpiles, and into the mills.
Great. Well, I'd really like to get a look at one of those stockpiles. Can we head up inside?
Sure can. We're going to put our PPE on before we go up there.
All right, well, let's get suited up.
Yeah.
You'd be surprised to find out just how refined the mining process has become. I'm at Teck Resources SAG Mill in British Columbia as we take a deep dive into the technology behind mining.
The ore enters at the top of the stockpiles and exits through the bottom. Within those stockpiles, we've got an arrangement of lasers looking down from the top of the dome down onto the stockpile. Those lasers are shooting a measurement, and we're taking that information from those lasers, computing it through a machine learning model, and giving us a volume of each stockpile at any given time. The volumes of those stockpiles, which we infer as height, were developed via machine learning models from the laser technology that we had installed inside the domes.
Well, Ryan, so I guess this is the next stop in the extraction process. We were just in the domes. We saw the material actually being loaded in, and it's actually sucked from the bottom of the dome and sent over to here. How does that happen?
That's right. There's a set of feeders underneath the domes themselves that's pulling the material down, going on a couple of conveyor belts, and it's falling into the SAG mill here behind us, getting ground out.
Now, once it gets into that tumbler, how is it actually ground up?
Inside the SAG mill itself, we've got a mixture of 5-inch steel balls and the rock, and those are all tumbling and actually breaking down smaller and smaller and smaller.
Can I get a look at one of those balls?
Yeah, sure thing.
So this is no joke. What's this thing weigh?
Yeah, it's probably 35 to 40 pounds.
Are all of the balls in the tumbler the same size?
It's a mixture of that and a little bit smaller. They get broken down and ground up smaller over time.
Okay, so now it's going through the tumbler, it's getting ground up smaller and smaller. What is the end game for it? Like, how does it move on from here?
In grinding, we're going to see everything come out of the SAG mill eventually. We're going to screen it off. Anything that's too large goes back to the SAG. The smaller stuff we'll send to the cyclones. In those cyclones, we'll actually send anything that's small enough to go to the floats right away. Anything that's still too big will come down through a set of ball mills, get further ground up until it's small enough to go to flotation.
And once it's in that float area, that's where the actual separation of the copper and the stone takes place.
Yes.
Now, there's obviously a lot going on here. There's a centralized location?
Yeah, the entire grinding circuit is controlled via control room itself.
Well, can we get a look at that?
Yeah, let's go.
Excellent. Well, I'm going to give that back to you. I don't want to carry that thing around all day. All right, let's check out the control room. So Ryan, we made it here to the control room, and Jesse is basically in control of everything that we just saw, the tumblers, the grinders, everything in the mill downstairs.
That's right. Jesse's got some visuals of the outside world where we started this morning, where we see the crushers and the conveyors, but he can't control that from in here. Where Jesse does pick up the control is when we see those SAG mills where we just came from.
Okay, now tell me what's happening on the screens here and how is he actually maintaining that control?
So Jesse's working with the HMI here, and he's controlling everything that we'd have from, like, say, mill speed or pump box level, and also seeing all the instrumentation that we have out in the field.
What does HMI stand for?
It's a human-machine interface, where we have, like I said, that controller piece between, machine and human.
Okay, now he's controlling everything right up until the flotation circuit in the process, right?
That's right. Jesse's doing everything he can to get that rock through the mill as quick as we can, and also grind it down as fine as we can before it hits flotation.
Okay, well, can we get a look at that flotation system?
Yeah, let's go have a look.
All right. Well, Ryan, explain to me how you make copper float.
Yeah, so we just came from grinding. In the last stages of grinding, we start adding reagents to the process. One of those reagents in particular is called a collector. That collector, once it comes over here to flotation, has begun coating the outside of all the copper-bearing minerals. From there, that slurry is being pumped down to the bottom of these tank cells in front of us, these two ruffers. At the same time, we're pushing air down to the bottom of this tank cell. It's getting sheared via an impeller to make bubbles. Those bubbles are floating to the top. And that copper-bearing mineral with the collector on it touches the bubble, it wants to stick to it, and it'll rise to the surface together.
So what we're seeing here, whenever that sloughs over the top of that, that's actually copper.
Anything that's coming over the top is the first sign of copper concentrate.
Okay, now I know that the ore tracking system, race technology, all of this is really important to the way you guys operate here. What's part of race technology is operating here?
Well, let's take a look over here. We'll look at one of the cameras. Here we see a flotation camera, or a froth camera, if you will, and it's starting to take measurements of things like froth velocity, how fast that velocity is when the froth is moving over the edge of the lip, bubble size, how much copper loading we're seeing on the bubbles. But it's one example of data that we start to feed into a database that race team then uses. And they're taking all that information, all that data, and using a machine learning model to determine where is the best point to run the circuit in order to maximize recovery.
Okay, so I know a few things happen to this after this process before it gets sent on its way. What else is going to go on?
There's a number of further refinement steps to try and make the best copper concentrate grade that we can. We'll remove any impurities or any other base metals we want from this concentrate. And then we're going to dewater it down to about a 7% moisture before we send it off to the silo, where it'll be loaded up on our trucks and head to Ashcroft and the drains.
Can we see it getting sent on its way?
Yeah, let's go see.
All right. So Ryan, after the separation and the drying, what happens to the copper next?
It's really the last stage for us. Once it's dewatering, it's going to end up at the concentrate shed here behind us and or the silo. From there, we load it onto pre-trained trucks and we truck it off site.
All right, well, this has been fascinating. I want to thank you so much. I'm getting back to Invention Land. Why don't you show me on out?
Sure thing, Greg. Let's go.
Hey, Greg, welcome back.
Hey, George, glad to be here. I'll tell you, Tech Resources and their mining operation were really fascinating. I was actually right out in that mine.
My gosh, it looks huge.
It is. It was very, very impressive. And even more impressive is their new innovative race technology.
Race technology. Okay, what's that all about?
It stands for Renew, Automate, Connect, and Empower. And basically what it is, it's bringing together engineers, developers, analysts, scientists, all getting together to make the mining process more efficient and more sustainable.
Sounds really good.
It is, and it starts right from the get-go. They actually analyze the ground before they even start to dig. And then once they do, that shovel actually has X-ray and other technologies that they use to analyze basically the rock. As it goes in, they know what the quality of the ore is that they're able to get out of it before they even start to process it.
In the shovel?
In the shovel. So now, as it goes into these fill trucks, that's a part of their OTS, or ore tracking system. So they know now, when they put it in their fill trucks to send off to their crushers in the SAG mill, basically they know what the quality of that ore is before they even send it on its way. So they make sure that the like kinds, go with like kinds. So so they have that pre-separation going on before they even start the next stage in the process.
More efficient.
And that's a part of this ore tracking system. So it goes into their crushers and basically ends up in these vats. And this is really fascinating. They use a flotation separation process. There's actually an agitator at the bottom of that vat that's stirring up air bubbles. They introduce some reagents into that water that then attract the copper to those air bubbles. So now they take a metal and basically make it able to float. It comes up to the top, goes through a sifter, and basically pours off as like a liquid amalgam of copper.
What a great technology.
It's amazing. And then it goes through a drying process. Once it goes through that drying process, it's ready to go. They load it onto trucks and send it on its way.
That sounds like a good trip, Greg.
It was great. It was it's copper mining for tomorrow's world.
Looking forward to our next adventure, Greg.
Me too, George. Thanks a lot.